Or this one?
The last one, the X.
The last one.
Because it says carbon dioxide combines with water in the plasma to form carbonic acid, but the equation is blacked out.
It's the middleman.
It's the middleman,
Yeah,
okay.
it's that one.
So you still got the bicarbonate in there as well?
Yeah, yeah. So that actually breaks down to form that.
Thank you.
This one here, this is sodium bicarbonate. This is when you take bicarbonate ion and you link it to a sodium. So it's just a compound that's stabilized by having sodium linked to it.
So carbonic acid makes bicarbonate?
Carbonic acid makes bicarbonate, right.
Alright, and then if you add sodium to bicarbonate, you get sodium bicarbonate?
Exactly.
And the sodium takes away the negative charge and gives it the positive charge right there?
Or it just gives it a neutral charge, no charge, yeah. Let me talk to you about the two examples up there on the top of 135 where you can add a strong acid or add a strong base. Let's use the example I mentioned to you earlier. Somebody who has a pancreatic disorder, they're not secreting enough pancreatic juice. So in their intestines, what they're absorbing is acid chyme. So of course, hydrochloric acid comes from the cells in our stomach. Here, let's add a strong acid, hydrochloric acid, HCl. Okay, so sodium bicarbonate is one form of the bicarbonate ion that exists in the bloodstream. But what you want to notice here, HCO3 is our old familiar friend. That's the bicarbonate ion that's acting as a buffer here. Have you had chemistry before? Do you happen to remember double replacement reactions? No? Okay. Let me show you what happens. If you've never had chemistry, or if it's been so long that it's just a blur in your background, let me just label everybody in this equation A, B, C, and D. This is square dance, and we're going to swing partners. We're going to switch them up, okay? So I added letters A through D on the bottom so you can figure out how we actually swung the partners for the compounds around. This is a double replacement chemistry reaction, and what we've done here is we've switched off sodium for a hydrogen ion.
Yeah, all of these are bicarbonate buffers.
Yeah, this bicarbonate ion here is your buffer, and it can take these two forms, these two here, can actually. It can create sodium bicarbonate and it can create carbonic acid. Let me show you what we just did down here. Which one of these compounds is acting as our acid? HCl, yes. Right, letters A and B together create an acid. You recognize bicarbonate ion, HCO3 there. That's part of this buffer system. Hydrochloric acid, coming from the stomach, we're talking pH 1 or so on the pH scale. If you absorb that into the bloodstream, you're going to bring your 7.4 blood pH down. And we're talking down to like 5 or even 4. So that's a drastic drop for your blood pH. What we're doing, though, in the bloodstream is the bloodstream can immediately make responses to that change in pH. So if hydrochloric acid is now in your bloodstream, this sodium bicarbonate that's in your bloodstream currently can do the square dance and switch partners. Now, instead of having free hydrogens floating through your bloodstream, look what we've done. We've locked them up with the bicarbonate ion, and we've created carbonic acid. Carbonic acid holds on to all the hydrogen ions that were being led off or secreted by hydrochloric acid. This is a strong acid, and it's more willing to give up or lose its hydrogen ions in solution. carbonic acid is a weak acid, is it as willing to give up its hydrogen ions?
No.
No, and that's the good thing here, because if you change a strong acid into a weak acid, you now have a compound that's more stable, less likely to cause problems with your blood pH, and we have now buffered this strong chemical into a weaker chemical, and this helps us to modify blood pH. And this is a very short-term process that happens immediately upon changes in your bloodstream. Look what we've also created. We've created sodium chloride, which is just plain old table salt. So we've made something that's fairly harmless as a result of this chemical reaction. So the key here is that we're using the sodium bicarbonate, switching it to carbonic acid, because the bicarbonate ion is acting as a buffer in this situation. Kind of make a little sense? This is some heavy-duty chemistry. Let's talk about adding a base into the bloodstream, because the result is the same. We want to buffer the pH change and prevent drastic fluctuations in our blood pH. So this time I've got sodium hydroxide, NaOH, there for you. Sodium hydroxide is actually released by your pancreas into your intestines. Let's say that you're taking a proton inhibitor in the stomach, you know, things like, what is it, Prilosec and
Nexium.
Let's say you're taking one of those acid reducers for your stomach. So your stomach pH is not really as low as it normally is, but you're still secreting enough pancreatic juice. That pancreatic juice is basic. Now we're going on into your intestines, and what you're absorbing is actually more basic than it should be. So instead of absorbing chyme that's, say, close to 7.4, we're now absorbing chyme that's maybe 8.5 or 9.0. So what you're doing now is you're bringing stuff into your bloodstream that's actually too alkaline for your bloodstream. In your bloodstream, you have this carbonic acid, and again, we do the switching of the partners. We do a double replacement reaction, and what we're going to do is we're going to take this sodium hydroxide and change it from a strong base into a weaker base. Stronger bases release more hydroxide, weaker bases release less hydroxide. So we're looking for a way to not have such a dramatic overall effect on our blood pH. So our result here is sodium bicarbonate in water. Sodium bicarbonate obviously is less alkaline than what we started with, sodium hydroxide. So here's the trick. Bicarbonate ions can act as a base. It can act also as an acid. I know in the past when we've talked about pH in courses, we've never talked about a chemical that can go both ways. You know, we've talked about something either strictly being an acid or a base, but depending on how carbonic acid or bicarbonate behaves there, it can actually behave as a base, which is sodium bicarbonate, or it can act as an acid, which is carbonic acid. Boy, is that confusing, right? Because you've got a chemical that can either behave as an acid or behave as a base. So it just depends on what it needs to do to blood pH as to how it may behave in your bloodstream. It can bind with sodium to form a base, or it can bind with hydrogens to form an acid. The good news is I'm not going to ask you to do these chemical compounds and all this mess on the test. I just wanted to give you the background so you have an idea how buffers work. But I know that a lot of you have not had chemistry. It's not a requirement for Bio 211. So this may be over a lot of your heads in terms of chemistry info. Hey, it's over my head not to have chemistry.
So that's the crap we did in biochemistry.
Yeah. crap it.
That's the kind word for it.
In the blood, you just have bicarbonate ion, but if the blood gets too acidic, it becomes sodium bicarbonate.
If it's too acidic, you become carbonic acid because you're snatching hydrogen ions out of the blood and you're attaching them to your bicarbonate ion.
Okay.
So they're no longer in solution.
And if it becomes too basic, it becomes sodium bicarbonate.
Yeah, because the sodium's coming from the hydroxide, sodium hydroxide. Julie.
Sorry to go there, but, so do you have too much CO2 in your blood?
That's where we're heading. That's the very next thing, so that's a very good question. Julie asked a good question here. Page 135, notice there's two mechanisms that will also help to accommodate for pH changes. So let's talk respiratory and urinary systems, because if you have, say, right this very moment, food being absorbed into your bloodstream from your intestines, you have to accommodate for those pH changes right this moment.